Hi, welcome to part 3 of our application layer module, and today I will try to talk a little bit more about HTTP, and specifically I'll talk about the application state, which the same thing as cookies. I'll talk a little bit about the proxying or data-centric view of the HTTP protocol, and I'll also talk a little bit more about the evolution of HTTP to HTTP2, QUIC, and the security of HTTP in form of HTTPS. So let's start with the application state, and I'll try to start in a slightly different way, saying that in HTTP, like in web browsing, you actually being tracked. So this is very interesting observation. So if you remember last time I mentioned that HTTP protocol by itself is actually stateless. So the protocol doesn't define any mechanism for you to track. Like it doesn't really remember two different requests coming from the same person, or like they're just two different requests. And yet all the websites can actually track you, and they do it very, very successfully. So for that, what was invented, especially on top of the HTTP protocol, is a mechanism called cookies. I mean, cookies, we like eating them a lot, but this specific types of cookies is something that client can set, or the web server can ask the client to set, and the client will have to repeat those things over and over and over again until they expire, or like some other conditions created for every subsequent request. So for example, as you can see on the slide, if you go on an eBay website or any other website that you normally do for the first time, you have nothing as part of the cookies. So you just go there, you send the simple GET request or whatever other type of request, and you've been processed. As part of this response, the server can ask you to set a cookie. And in this specific case, it's asks you to set this 1678 value, and this value is absolutely the server specific and kind of have no other meaning or any kind of interpretation kind of in HTTP protocol. It's just the application decides what it wants to set, and it's being set. And what is required from the compliant client is then is to respond or like include this cookie as part of any future request. So for example, if you go to the eBay for the second time, you include that cookie, and this is how the web server can actually remember that it was you who kind of to match these two requests together. So the first, the second, and the third, and subsequent one. And this is exactly how like, effectively all web applications remember that you already requested some information, and it's effectively and essential for the authentication purposes. So for example, if you go to the bank website, you send some form of a PUT request with your username and password, then the bank creating some secret session or something like that, setting up a certain amount of cookies, like requesting you to remember some amount of cookies, and every subsequent time when you're accessing the same bank webpage within whatever time limit, then the web browser simply keep sending that cookie, and this is how the server is remembering that you already logged in and doesn't require you to log in over and over and over again. And to give, I mean, on the slide, there's also additional ideas of how exactly this operates on the web server side. I mentioned there's a database backend, but how exactly it's organized is really up to the web server application, and there's no HTTP definition how things are working. So this is effectively the very great mechanism for the application state, but as I said, it's also being used in a slightly different way. But just to give you additional thing for the cookies operations, so effectively there's a website, there's a browser. Whenever a website is mandated to, whenever a website is trying to send a request, it actually have an internal database of different cookies, and if it knows that it needs to add additional cookies as part of the request, it actually creates additional HTTP header, like the one that we looked in the previous part, and add whatever value that was specified by the server. Just additional small comment: the cookies, even though they're designed to be provided by the browser, by the website, by the server, the browser on its own can also define some of the cookies. So, for example, if you run in JavaScript application, like the server gives you a JavaScript application, that JavaScript application can technically give you some amount of cookies, can set up some amount of cookies, and then like for the subsequent request, the browser will be repeating those requests. Yeah, so as I mentioned on the website, there is some form of a local database on the browser. There is some potentially database on the website side, and what this database is, what's been remembered, is up to specific implementation. Just to, I don't know whether any of you have played with the PHP. PHP, there's one call you can make and which will result in creating a state for the client and effectively giving the client some information like this command to set a specific cookie, and it will be remembered for the future requests. So this is how, like in PHP, you can easily create some form of a session without actually doing anything. Like everything else is technically provided by a framework already. I have mentioned already that cookies can be used for the good part. So like it's essential part for the web's authentication mechanism to record that you have been already logged in a system. Like whenever you go to the Google search or like a Gmail, you don't type your password over and over and over again, because it would be really daunting if you had to authenticate yourself for every single HTTP request. So that's the good part. However, there's also a bad part of the cookies, and with cookies, especially when they're used in a slightly negative way, like with some tricks, cookies can be used in not a good way. And one so-called not a good way is actually so-called advertising. I'm absolutely sure that I'm sure you used Amazon in some way, or at some point in your life you may have purchased, you look to buy, let's say, the cat food, and so you Google cat food, you went to some completely random websites that sells cat food, you looked at different types of the cat food, and maybe or maybe not you actually purchased something, but it's irrelevant for this conversation. And in next 3 days, you suddenly start noticing there's on a bunch of completely different websites, you see advertisement, and those advertisements somehow include the information about the cat food. And who knows, it's absolutely you never went to this website, and yet you're getting the advertisements that are tailored towards you, because you was interested in the cat food at least a couple of days ago, but the websites are remembering about that. And you can thank or blame cookies for this part, because there is some advertisement companies, and I'll show you in a few moments later, they actually abusing the cookies in order to record what have you requested before, and use that information later to give you some additional suggestions based on what you have requested. So in Europe, they created this GDPR law that actually forces you not forces you, but rather forces website owners to give you option to opt out, or at least acknowledges that you are being tracked if you go to the specific website. And I'm 99% sure that you went to some of those websites and you had to click accept something about the cookies, so you're being tracked, or some specific phrasing of that. And again, this is the cookies, they can be used for good, but there are, the advertisement company is not necessarily bad. They just companies whose business model is to track you and provide you some form of a suggestion based on your past behavior. And to give you an idea how this thing is supposed to happen, you need to remember that the single website is not really getting all the information from one server specifically. So for example, if you go to like website one, like example1.com, it doesn't mean that all content on this website coming from that specific host. In many cases, and I think in majority of the cases, the content is coming in a bunch of different places. And one of them can be this tracking company, like @foxytrack.com, like this is like a phony one. And if I give you the real one, Google AdSense. So those guys, they actually they're providing service for the website owners, but they're also having some ability to track you as a user. But in any case, so when you go to that website, and then there is a small script that been fetched, or there in some way something been fetched from this @foxytracking.com, and in this process, that website is adding you a cookie. You're not going to, this cookie is not relevant to the example.com website, and I'll show you in a few seconds. There's very strict restrictions of what kind of cookies has to be associated with what websites. But it's still, this cookie just related to this foxytracking.com, like actually to add the foxytracking.com, and only being supplied when you go to this website. And yet, if this company is big enough, it is foxytracking.com big enough, and convince another website to also include information, like some fetching of something from the foxytracking.com. It can be a script, can be image, or like fake image. There are multiple mechanisms what people are doing. Then the same cookie will be sent out to this @foxytracking.com with additional information that you actually on a different page. So there is also every time you send a subsequent request, the browser are nice enough to include information about from which page or from what is a previous request is associated. And if there's a very elaborate JavaScript, that JavaScript can actually scrap the whole page and send it to the @foxytracking.com. So this is how it knows more and more about you and learning your behavior, learning what you like to purchase, what you're searching for, and so forth. So this is the basic mechanism. So there is the same piece of code injected at multiple different websites. You go to different websites, but you've been tracked by these third parties that effectively they built some form of a tracking history of you. And there's tons of different bizarre behaviors of these third-party companies. So some of them actually know more about you. They have estimation based on what you're requesting, which website you go in, what you're purchasing. They actually can estimate your sex, your age, your social status, and so forth. So this is really serious stuff, and that's why that European law has been passed. To add to mechanics of the cookies, so there's a two opposite parts. So one part is a request to set cookie, and then the part of actually supplying the cookie. So one of them is reasonably simple, and the other one becoming, actually they work together and becoming more and more complicated. I'll give you some examples at some point in the lecture. So the first one is set cookie. So the set cookie in the simplest form is just giving you the value, and whatever the application specified, like the web server application specified value, and that value will be reflected in a subsequent request. But in addition to that, that set cookie can restrict, it can specify to which domain name this cookie belongs to. So it can be just a domain name or a parent domain name. It can restrict this cookie to be applied only to a specific path. So for example, if you go into /login page or /user space or /something, so the web server can restrict that this cookie is only sent out to requests that have this specific path. And there are additional fields like expires, max age, that define how long this cookie should exist in the browser, on the browser side. And the other ones is just additional security implications that this cookie has to be can only transfer over like secure connection. This cookie can only be used to request something like the only HTTP page, or I think it's about HTML pages, because there are some tricks that like when you're fetching an image, you may not want to include the cookies in those cases. So the part of the cookie itself, like that been responded by the browser, and the reason I said it's a little bit complicated, because the client has to process the request properly and in kind of in a secure fashion. Because what can be done in non-trivial, so first of all, it has to kind of process all those flags, whether it's a secure, whether it's HTTP or something else. Then it has to make sure that the cookie has not expired so far, and then it has to apply various restrictions. So the simplest one is the path restriction, because that's the path, and a little bit more complex is the domain restriction. And let me give you two specific ideas regarding these cookies and domains. So the path, as I said, is very simple. If the server can say for this path, use this cookie. If path is not present, just use for all paths whatsoever when requesting for the server. So that's simple. That's quite clear. For the domain not specified and domain specified, then there are two restrictions. So first one, if it's not specified, then the cookie is only applied for requests for this domain that you went to. So if you went to www.foobar.com, then the cookie will be only set for this domain name and nothing else. So it's not going to be set if you go to just foobar.com or if you go to the bar www.foobar.com. So that's not the case. If you specify the domain, then in that case, the cookie would apply for the domain itself and any subsequent subdomains. So, and I gave you a few examples on the slide. However, the browser community, like all this HTTP community, defined that defined what client can actually specify. And the client cannot specify the domain name that is more specific. So somehow it cannot specify that the cookie only applies to the subdomain bar www.foobar.com. So this is not allowed. Even though if you define, like if you set the domain name www.foobar.com, the cookie will be sent out to that domain name if you go there. But you cannot, the web server cannot restrict the cookie to be only for that subdomain. At the same time, the browser allowed to specify cookie for the parent domain name. So this is a little bit counterintuitive, but this is what is allowed. So for example, if I'm going to www.foobar.com, the server can tell me that I need to set a cookie for for foobar.com. And effectively, this cookie will be sent out with every single request, be it foobar.com, www.foobar.com, www.foobar.com, or anything else whatsoever. There are a few restrictions for this rule. So, for example, if you just went to the foobar.com and the server tries to set a cookie for .com, so this will be restricted, and there's a rule for the public domain names. And there are a bunch of more besides this .com, but just think something very, very public, something high level that not supposed to be used by the private company is restricted, but everything else is a fair game. So I will try to include the one homework specifically about the cookies, so stay tuned about that. So as regarding the security, I mentioned it can be used a little bit for evil. I mean, it's used for good, but sometimes it can be used a little bit for evil. And one specific, I gave you two examples on this slide. One is a session hijacking, and the other one is a cross-site request forgery. So in one case, what we're trying to do is the bad guy, what is trying to do, it's trying to steal your cookie. To do that, it's not. So this one is not really trivial to do. Again, don't get right away scared that oh my gosh, like you have to disable all the cookies. And by the way, you can't do that. What needs to be done is the bad guys needs to convince you or convince the website owners, like good website owners, to inject some code, some bad code. And for example, this can happen sometimes when the website is compromised and some bad code is being injected. So that's a kind of a primary mechanism. Less primary mechanism if there are a bunch of websites where users can input some additional comments, and in extreme cases those comments not properly sanitized, and bad guys can inject some form of a JavaScript, so other users and then hack the server effectively, and so the other users will execute the code of the bad guys. So that's how this piece of code potentially can get into. But what's effectively going to happen is this bad code that is in a legitimate page simply encodes all the cookies that the browser knows about. This like easily accessible from the JavaScript, specific to this web page, and then sends it to whatever website. And this cookie is really essential for the session. So for example, if this is a bank website and you have logged into this website, having all the cookies associated with the bank domain at this point of time would be equivalent of being logged into your bank account, and you can do everything whatsoever. So that's the kind of danger of stealing cookies. This can be used for good as well. It's being used for the good part, but this specific hijacking or specific stealing is related to the fact that if you have a session, this session can be stolen through this third-party code injection, and after that, anything can happen to that, to whatever was stolen. So the second one works in slightly different way and working in a different direction. Is it doesn't require the bad guys to compromise the good website. So the first one requires that one, but it's simply kind of creating a bunch of bad websites that you accidentally or by some unintentionally go to. Like sometimes you Google some information and like a bunch of links popping up, and you just open different pages. Unintentionally or intentionally, and those web pages may include some of the bad code. And the code is not that, it doesn't look too bad. In general, it's just trying to fetch a fake image from the website. There's no image associated with this website. It's actually a normal web page potentially, but rather it's just abusing the mechanism of the HTML to send the request, to simply send the GET request, and whatever, it's not going to be properly interpreted, so you're not going to see any output. But rather there could have some kind of side effect on the bank side could happen. And in this case, what is kind of the bad guy is trying to achieve is trying to withdraw some money from your account. And how it happens? Just because when you send this query, the browser will automatically attach the cookies associated with the bankexample.com. And if you happen to log into the website already, and if you happen to kind of still be logged in and have an active session with the bank, then something bad gonna happen. Don't worry too much about the bank. There's a reasonably good restrictions and reasonably good separation between different tabs, and bank administrators, bank developers have a reasonably good job in limiting the cookie for the lifetime of the tab. But in general, what is recommended for the security purposes, if you open a bank account web page and kind of done doing this whatever stuff, you better close that web page, close that tab. You don't need to close the browser, and start your process in a different tab. If you close in the tab, it automatically effectively clears up some of the cookies that the bank that was created during the session with the bank. And whenever you open the new tab, there will be no associated cookies. And when you try to go to the bank site again, it will try to log in you again. And if you don't, then you potentially is vulnerable to this cross-site request forgery. Okay, I hope I scared you enough. Cookies are good, cookies are bad, cookies can be bad, cookies can be good as well. So, but effectively they implement the application state at the implementing some form of application state. Now moving to a different topic. I mentioned the HTTP protocol is data-centric. At least I used this word a couple of times. And what I mean here is the protocol by itself, in normal circumstances, just uses this URL that I introduced last time to request some piece of data. And if we're talking about the GET request, this is what's happening. I'm having a URL, I just create a simple GET request, I send it, I got response back. I send it, I got response back. There's a few complications with I just introduced cookies, for example, because now two requests not necessarily the same. They potentially have some side effects. But if we, for a second, forget about those things, it's really the protocol itself is very stateful, no state associated. There is URL, so then we can do something about that. And what we can do proxy. So this is very interesting and very, very powerful mechanism that is still exists today. It's used in slightly different way as we'll talk more. But effectively what is happening in the system is instead of communicating directly with the origin server, like for example, I don't know let's say it's Amazon.com, though I'm not sure what exactly is that web page. We can communicate with HTTP proxy or the proxy server, and receive exactly the same response. And what will happen is I'm sending requests to the proxy server, and I'm just connecting to the proxy server because that's what I know how to communicate with. As part of my request, I specify the URL. I mean, it's in different parts, but effectively the whole URL is inside the HTTP request. And the proxy server, instead of giving me results right away or processing this request as an application, it simply relays that request to the origin server. I mean, it simply figure out from the request where it needs to connect to, which TCP connection it needs to create, connects there, copy pastes the whole request, and hopefully that origin server is processing as normal application, returns the response. Things can get a little bit more complex in the system is when the origin server is by itself a proxy and it has internal redirection to the more specific server, and that more specific server is also redirecting to somewhere else. And this is actually reality in today's complex web applications, but you can think of there's just one layer of indirection. So I said that the proxy server can relay your request, but that's not the only thing that proxy server can do. And the whole objective for this proxy server is to cache already existing requests, or the object that has been already requested. So for example, if there is some very popular cat video that's been requested over and over again, then the proxy server simply can cache those objects, and whenever it sees request by the whole URL that you're specifying, it can simply reply to that request right away without contacting the origin server. So that's the main idea for the cache. And there are a few good reasons why you can do that. For once, it significantly can reduce the load on the origin server. And it can reduce the traffic load of the network itself, and effectively it can speed up the response time for the client. I would like to make one note and get back to the previous slide. So this proxy server in today's environment actually exists on the web browser itself. So when you go to any web page, the web browser has its internal proxy server. I mean, it's not called a proxy server, it's just called some form of a cache, but there is something internal to the web browser that is pretty much the proxy server. And then whenever I'm requesting, or some other element inside the web page is requesting for some resource, first thing is happening is the browser will check its internal cache, and if it's there, it will immediately return without ever sending any kind of request or DNS queries or anything like that. If it doesn't have there and the system is configured to use proxy server, then the request will go to the proxy server. You may get response from there. If not, that proxy server making request to the origin server or origin destination, and that origin server either gives you a positive result, negative result, or kind of further relays the query to the next level proxy, for example. But it's kind of interesting mechanism in all possible because of this data centricity and technical statelessness of the HTTP protocol. There are a few examples I gave you on this one and the next slide, just to highlight the fact that without caching, and if you want to support a certain amount of users, you need X amount of resources, and you can go do these calculations on your own when you're reading the lectures. And if you enable bandwidth, to solve the problem, you can simply buy more bandwidth to serve more resources, or simply add in some form of a local caching and satisfy the same amount of kind of requests with some probabilistic model with the same small capacity. If you remember, I think in the first module, I mentioned something like this before, and I would like to ask you and like you to remember and tell me what exactly I mean by this, because I already mentioned the fact probabilistic way of serving more users than you have available resources. And so in this context, it's about the cache. So the local cache is kind of pre-caching some requests, and if for something popular, it's serving them together. I have been using the same phrase in completely different context. It was about internet itself, but it was different context. Please tell me what it is. But having a cache, having a local cache is not free. And then, for once, it needs to be configured. So if it's not just kind of inside the browser cache, if you want to have some cache to be configured from a local server, it needs to be configured in the system. Sometimes it's easy, sometimes your local DHCP server is actually providing you this information, or sometimes you have to discover it on your own. Just a side note, it's not used too much today, like in the form of institution proxy, but it still exists. I think FIU still may have the proxy server, and I'll get to that in a second. The biggest problem, so the last problem I'll attach to later, but the biggest problem is the obsolete information. So this one is a really, really huge problem, because you have to know how fast and when exactly you want to remove the content, or refetch from the original producer. So for example, if you're talking about the CNN.com webpage, when I went there for the first time, yesterday, for example, and the proxy didn't have any content about CNN.com, and it fetched on behalf of me the version from yesterday, I really don't want to receive the same version today, because it doesn't really make sense for me to read yesterday news. So if I wanted yesterday news, I would go to this specific section on the CNN website to read the yesterday news. But the URL on its own doesn't really identify that I want to request today's news, because it's just URL cnn.com/ that's it. So there has to be some mechanism embedded as part of this HTTP headers, HTTP responses, HTTP queries to ensure that I'm getting the kind of latest content, or the content that I think is reasonable enough. So that's one problem. And the other problem is HTTP security. I'll try to touch it a little bit later, but effectively, when we're trying to establish the secure HTTP connection, we cannot do it through institutional proxy. And for one specific reason, if I'm trying to connect to my bank website, I want to make sure that I have connected to the bank website. And there is a cryptography mechanism that kicks in for this part to ensure that the other party is the Bank of America, or like Bank of America, or Wells Fargo, or whatever, or some other bank. My local, if we have a proxy inside a FIU or somewhere in your ISP, that proxy cannot prove you that. It doesn't have authority over the bank's website. So therefore, there is a basically impossibility to run proxy for HTTP, secure HTTP. There are some workarounds with respect of, there are no workarounds for the institutional proxies, but there are mechanisms that those websites still use a form of a proxying. It's not exactly the proxy server that you deploy, but rather it's a proxy servers that the Bank of America or Wells Fargo or Netflix are deploying, and they give proper authority for the whole namespace, for the whole kind of bank or the Netflix data sets. So in those cases, when they give authority, when they deploy those servers, they can act as authority, and you kind of, by connecting to them, you will think that you connected to the actual server, even though you may be connecting to some intermediary. But that's what's the current workaround, as I mentioned. But for the obsolete content, there's additional thing that exists as part of the GET request. And there's one specific header, and there are a few responses, is to make sure that you get what you want. Like that it's not, you want to get the most recent version of specific file. And specifically, you can have this conditional get. So effectively, it's either done by your browser to the web proxy, and can be done by the web proxy to the whatever origin server. So whenever you request information and you already have a local copy, you can send requests asking, give me some information if it wasn't updated since this specific date. So it doesn't really identify the specific version, but it kind of approximates the version using the date. And if content was not modified since that date, or like the version, effectively version, you have the latest version, then the response will not include the actual content. You're still going to get response for that, but it will only include this 304 not modified header, and you don't need to do anything. You can just respond simply from respond with the cached version. If the object was modified or the versions don't match, or by whatever reason the server doesn't want to process this header, then you will get the whole package, that whole data package back, and you can cache that version for the later use. And again, so this process exists internally inside the browser and exists internally inside of the web proxy, and potentially in some this kind of not institutional, but the application deployed proxies. And we'll talk more about this as part of the CDN, or content delivery networks, in one of the next parts. I think I already talked about this one. It just kind of reiterate that the proxy, as they were defined, even like, or were used about 10 years ago, is not exactly the same today because of the use of HTTPS. That's one of the primary reasons. And in general, the links are getting faster, so we're not getting stuck like inside institutional networks. Kind of, we're not really constrained by those things. For example, in FIU, I think we have like a gigabits or tens of gigabits of bandwidth available for us to use. So it's kind of not a big problem. Now the problem is most likely on the other side. So that those applications, they really need to process a lot of requests that is coming faster and faster. And the concept of HTTP proxy is used today in, as I said, in a slightly different way. It's more like it's like, again, it's not a reverse proxy, but rather it's a proxy that exists on the application side. It's not, I mean, it exists on the browser side, like internal to the browser, and it exists at the kind of remote side near the application, just to make sure that if it doesn't receive too many same requests, it doesn't need to do very costly processing. That's for one reason, and potentially it can do dispatching requests to multiple replicas of the same server. And I mentioned that some universities still use HTTP proxying, and I think for FIU you can use it as part of the library. There's a library proxy, and you use that proxy to get access to some of the library material that is being used, only available if you're on campus or if you're using this proxy. It's not exactly VPN, and we'll talk about VPN more, but it's some simple form of a VPN. So the next one I would like to talk about is improvement of HTTP. As I put on the slide, even HTTP 1.1, with all these improvements of this pipelining and persistent connection pipelining, it's still not fast enough, and there's a few mechanisms that needed to be in there. So for once, so this is just one measurement that I stole. I forgot. There's some research paper that did analysis of kind of average web application, like average website. So they found out that this average web page is actually not a single file. I already kind of highlighted this a couple of times. But on average, it consists of about 90 objects. It's a kind of huge thing. What is not really expected, or was not really expected from these 90 objects, is the fact that they come in not just from a single, not from two places, but rather on average or from 15 different sources. So it's kind of really interesting. And kind of the total size is a megabyte, and I think this research was done some years ago. So I would say now the amount of data being transferred is significantly more. And on average, there is also, you can see there's a much smaller chunks of the page being retrieved. Again, some objects are large, like some images, but there are tons of very small things like script here, script there, some CSS files, and so forth. So what we can do? So one thing what we have to do is to enable pipelining. So even though pipelining is available as part of the 1.1, HTTP 1.1, it somehow was not enabled by default. So it's still an application as a browser. You have to explicitly enable it by using the specific header in there. And then in that case, it will be used. But it's, again, not available. So some people did know about that. Some web browser didn't properly implement that. And because it has to be also implemented on the server side. So it took some amount of years for this implementation. And so one workaround, and I have actually experienced this one during development of some of the applications that I did on web. I don't know if you did web development, you may or may not have done this before. Sometimes what people did to avoid to speed up the process and leverage some kind of a caching. So if a website has a kind of design of the website consists of many small pictures, what they could do is to put all those pictures in one big picture and preload this picture using the JavaScript, and then as part of the individual pictures placed in a visual environment, they can simply reference a part of that big picture. I mean, it's very easy to do with the CSS, like a style sheets. So you can do that, but effectively this is not the solution, but rather a workaround of the problem, because getting a lot of small object was really costly versus getting one object and pre-cache that object. No longer true today, but that was the case a few years back. So the second problem is Headofline blocking. So this one is a little bit more complicated, and I will refer this again a bit later. But in this specific case, it's about the blocking, how to say that? So let us remember the pipelining mechanism. In pipelining mechanisms, you issue multiple requests, and you can just simply waiting for all this kind of requested objects to come in one by one. So, for example, if you requested a few small things, one big thing, then again a few small things. So now you're gonna get a few small things fast because they're small things and you can just get them one by one. Then you have to wait the whole amount of time until the big chunk being delivered to you, and then again you can get your small thing. So that's kind of the problem of HTTP 1, because you request everything in the pipeline and you receive everything back again in the pipeline. So one of the solutions that the HTTP2 was proposing is to do some form of a chunking. So instead of kind of making requests to be fulfilled one by one, like in a pipeline, but one by one, all requests can do some form of a round robin. Like you receive a little bit of the first response, a little bit of the second response, third response, the fifth response, and then again, like by whatever order you kind of the server decides to send you those small chunks. So this way you can avoid some of the problem of this head-of-line blocking. Again, this is not all problems. There are some additional problems. I'll try to talk in a few moments. There's another big issue with HTTP, HTTP1, HTTP 1.1 is a lot of redundancy. I highlighted, I think when I started talking about HTTP, is the protocol is human readable, but it's kind of a little bit stupid. I mean, back in the day it was meaningful because people really were writing those requests by hand sometimes. It's easy to debug such an application and easy to write a new application. But talking from today's perspective, it's really not efficient to actually process those requests, because now you have to read the whole line. You actually need to find this /r/n to figure out the end of the line. You need to process all those headers one by one until you receive empty line, and then do some form of a processing. And besides that, besides this processing issue, the text is not the most optimal way. So for example, there's same requests, same headers, same keywords being repeated over and over and over again, and they take significant portion of space, but you cannot do anything for the protocol perspective. So the HTTP 2 tried to address this part. So what HTTP 2 decided to introduce is simply binary framing. So instead of doing this standard post or get request as part of and using the human readable ASCII text, it simply did some form of a binary encoding of the headers. So it's a very different way of representing the same request. I mean, semantically it's same information, semantically it's same request, but for very common keywords, you don't need to specify host versus it's recorded as some specific number representing this header. And instead of writing literally post and a version of HTTP as HTTP2, it will be some few numbers as part of the header. You still need to specify the full URL, like for example the path, the host name, potentially the content type. You also need to specify in full, but the rest can be optimized in some form. I'm not going to go into detail of how exactly it's been accomplished, but just remember that it's no longer like when we're talking about modern HTTP, kind of HTTP2 or QUIC that I'll be talking in a second. There is no longer this legacy ASCII requests, but kind of the web servers still support even the HTTP 1.0 that I demonstrated in the previous part. And kind of in any case, the HTTP 2 request with whatever compression mechanism and HTTP 1 or 1.1 request, they effectively equivalent. It's just one is more space optimal than the other one. And the second part is kind of effectively addressing the fact of this head-of-line blocking. So as I mentioned, instead of a simple response that's been returned you as a one thing and you processed it as a one thing, there's a concept of a stream. So all the responses have been chunked in probably the equal size data. Yeah, okay, I wouldn't use them data packets, but rather small chunks of frames, like the application frames, and being delivered to you. And you, as an application, as a HTTP kind of processing application, you decipher them, assemble into kind of the complete messages, and as soon as they assembled, you deliver them to the application. You can play with additional things like priorities of those messages, like which effectively define how often you would include some specific responses as part of this intermixing of different messages. But that's effectively it of what I want you to remember. And to summarize what I want to say, so HTTP2 gave significant performance improvements compared to the previous protocol. And the first one is binary encoding and header compression. So for one is you're trying to reduce amount of redundancy as part of the kind of repeating the same keywords, like the very common keywords. That's once. And the header compression, you simply running some very simple compression algorithm to even compress the request. So I mean, this one is some form of a zip or something like that. And the second part is kind of using TCP connection in a slightly different way. So instead of using it as a kind of stream of one thing being delivered, you intentionally split what you're transferring with that TCP connection into smaller chunks and kind of deliver those chunks back to you. So it's kind of significant improvements, but not good enough. So there was additional development, like additional discoveries, and there's a new QUIC protocol that it's still being designed, but if you are using any of the Google services and if you're using Chrome browser, you're actually using QUIC protocol instead of HTTP. And what things is embedded as part of the QUIC? So some things I kind of put on this slide is a little bit ahead of what I'm talking before, but if you finish watching this lecture, you'll know a little bit more what I'm talking about here. So first of all, HTTP2 still inherits several problems. As I said, I will talk about Headofline blocking again. So even though HTTP2 solved some of the Headofline blocking, it didn't solve the TCP's Headofline blocking. So what has been solved is application Headofline blocking. So when I said like instead of delivering big messages, you split things into pieces and deliver them individually. So what I'm talking here, this TCP problem, is the fact that TCP is reliable transport, and it will try to deliver every single byte as kind of in order and will not release it to the application until it was received in order and in sequence. And even though you're trying to intermix different pieces as part of the stream, kind of you send this instead of big chunk, you put in a small chunk. If you lost a few packets, if you lost a few TCP packets, the TCP itself will delay everything. Like there will be small chunks, but they will be delayed by the amount of time you recover some specific packet. This is the smaller problem than the original Headofline blocking of the HTTP 1.1, but it's still a problem. Like especially if you're on a bad connection, it's still quite significant problem. The second problem, okay, maybe it's not exactly a problem, but it's a challenge. So the congestion control. We'll talk about the congestion control in more detail as part of the next module and as part of the project too. But effectively what I'm trying to highlight here, if you're using TCP, this congestion control is built into TCP, and TCP is built into operating system. And if some application wants to try to use different congestion control algorithms, like experiment with some different congestion control algorithms, it's effectively need to convince every single operating system to implement this congestion control algorithm and kind of wait until all the system getting updated and kind of start supporting them. So it's basically almost impossible to do that. And just as a side note, all operating systems actually use different congestion control algorithms. So like Linux is different from Mac, is different from Windows, different from FreeBSD, for example. And what QUIC is trying to do is trying to use congestion control mechanisms at the application layer. So the second part is the TLS, or like security layer. So normally, I think I actually highlighted in previous part, there was a non-trivial delay to set up a TLS or SSL connection. And this is one piece that QUIC is trying to do. So again, normally what's happening, you have to establish TCP connection. Okay, let me start even before that. You have to make a DNS query to figure out IP address. You have to establish the TCP connection, and on top of that TCP connection, you establish a TLS connection, and then you're ready to do some kind of queries, HTTP1, HTTP2, or whatever. If you go to the same website again tomorrow, you have to do the same thing again. You may be skipping DNS part because this part can be cached for a couple of days, so you don't do DNS query again. But you still have to establish TCP connection. You still have to establish the security property, this TLS session, and then you're ready to send a request. So with QUIC, they try to optimize this part. They also optimize the establishment of the security. And for one of them is instead of every time you set up the security session, you actually remember some of the security properties from the previous connection that you made, and simply when you go to the same website again, you're reusing that information. So that's kind of one of the solutions. And as I mentioned, I didn't mention yet, but I mentioned about the congestion control. So the QUIC is implemented on top of UDP. So it's QUIC by itself is implemented on top of the unreliable delivery protocol, and itself trying to provide the kind of this reliability guarantees. So it's effectively trying to implement some form of a TCP on top of the UDP, and this is exactly what we're going to be doing as part of the project too. And while doing this operation, they can implement their own flow control, they can implement their own congestion control, and do whatever they want as part of kind of this application. And they don't need to convince anybody, like any operating system. They just need to convince the web browsers and the web servers. That's it. And kind of Google is powerful enough that it controls its own Google infrastructure and Chrome browser. Another one that's been improved, as I said, this head-offline blocking. So because they use this UDP and their own mechanism to process the flow control and congestion control, they actually embed those the concept of the streams as part of the UDP. So they no longer put kind of all those streams in a TCP connection that being kind of one continuous stream, but rather have a concept of multiple reliable streams within one connection. So it's just a kind of additional mechanism on top of the like beyond the TCP. And like in the simplest form, you can think of this as a in one QUIC connection there are multiple sub TCP connections. And the last one, that is one of the last items mentioned on the website on a slide, is error correction. So for example, when delivering videos or delivering some traffic, QUIC can add additional bits to the headers to ensure that within low rate of losses, everything can be recovered even without retransmission. And the last part, the connection migration. We will touch this one a little bit later, like when we're going to be talking problems of TCP, but just to highlight, maybe you experienced that before. With TCP, whenever you disconnect from Wi-Fi, move to LTE, move from LTE to Wi-Fi, your TCP connection breaks. And kind of if your application was dependent on that connection to be alive, nothing good gonna happen. So for example, if you had SSH while you were on the Wi-Fi, you disconnect them from Wi-Fi, move to LTE, that SSH session no longer exists. Like it doesn't, I mean, it's probably gonna break in a minute or so, but it cannot continue using LTE. And with QUIC, they actually added a few elements to have ability to transition the same connection to a different network environment. So no longer depend on how you connected from which interface, from which IP address. There are a few more details, so I think you can try to learn a little bit more when you're looking through the website, and I also include a few links about the QUIC as part of the additional reading. But I think I already covered most of these things. This very interesting approach, like a very interesting optimization of HTTP. I already mentioned multiple times this magical thing HTTPS, and it simply means secure HTTP. It's something that is ensured that it's you're talking to the right place, and your information that you're sending cannot be observed by anybody else. And this reminds me one interesting task that I would like you to do, like at least try to do it. So I think you have played with Wireshark already, and at least I hope you have played with Wireshark. And Wireshark has a great ability to reconstruct TCP streams. And what I want you to try to do is first find out non-HTTPS website. Unfortunately, it's in modern days, it's a little bit challenged to do, but there are some websites that not protected with HTTPS. If you have a challenge to find such a website, please contact me and I'll try to find you some. And then try to run Wireshark and sniff while you connecting to that website. And what I want you to observe from that exchange is the fact that you can see everything. And by you, I mean you as an end host and any router in between, any kind of maybe host that is very close by to that router, they can actually see all the traffic going on. They can reconstruct everything what's going on. And if you somehow send in sensitive information as part of this HTTP request or some form of response, that information can be easily stolen. So that's why all the browsers warn you if you try to send a password or like send a put request over to HTTP website, and they will tell you, oh, you're gonna try to send something over a non-secure connection. Is it just because that information can be so easily stolen by somebody else? So you better not do it. And as I said, there's basically all websites today that being deployed are using HTTPS, so it's kind of reasonably good with a few exceptions. And I'll try to get a few exceptions. With secure HTTPS, you're trying to ensure that you go into the website that you intended to go. And for example, in some cases, when you go to the website, you will see either green information, like there's a lock with some information about who this website belongs to. Yes. Whenever you see the lock, it simply means that this website is protected by the HTTPS. So that's good part, and you can be almost sure that everything is fine. But you still have to pay attention to the URL and some messages that your browser may pop up and tell you about this website. So there are different representations of kind of security, and to ensure validity of this connection, the website owners can go through several processes. So one of the simplest processes is they can ensure that they can request certificate to validate that this website belongs to this domain name. That's all. So this is like the so-called the domain validation certificates, and they only validate that someone who serves this website from this URL is the one who serves the website from this URL. It doesn't tell you anything about this company. Sometimes it's enough, like in actually majority cases it is enough, but there is also different type of certificates that I just show you with the Bank of America. They're called extended validation certificates, or like simply put is EV certificates. So in those cases, there's additional assurance. It's not only a statement that this website is being served by the kind of guy who knows this domain name, but it also associates this website or this domain name to real-world identity. So in this specific case, it's stated that www.bankofamerica.com is actually Bank of America, like a Bank of America corporation. And if you open details of that certificate, you actually can see the address, potentially phone, or some other identification information. Because sometimes it's obvious, sometimes you know the URL, and sometimes it's not obvious. This problem is less and less in existence, but a couple of years back, Amazon.com was actually adding the certificates, adding the security to the website as optional feature. So some parts of the website were just completely unsecured, and some of them were secure. So, for example, if you were just browsing without being logged into the website, it was completely unsecured. As soon as you tried to purchase something, it added the security component. So my recommendation, just pay close attention. If you somehow got to the website that is not HTTPS, just try manually put the HTTPS in front, and hopefully it works. And if it doesn't work, try not to go to the website. If you have to go, okay, so then there is no other choice for you anyways to do. As I said, you can check manually the status of the certificate or information about the certificate. And one important note you can try to see is who exactly issued the certificate and what the certificate was issued for, and there's a validity of the certificate. So the example I'm showing here is, I think, Mac specific, but similar information available on all platforms, and it's easily accessible from if you kind of some form of a clicking, is it the right clicking on this lock icon, and then there will be information about the certificate. Just to give you interesting note, so the certificates are issued by this so-called the certificate authorities. And there are around 100 different certificate authorities that can issue a certificate for any website in the world. And you simply or implicitly, by installing the operating system or installing a specific browser, you simply implicitly agreeing that you trust those 100 magical authorities. And I mean, they don't usually do bad stuff, but you have to be aware that there are at least 100 of those guys, some of them in the US, some of them in like different parts of the world, and all of them have the same power to do this certification of different websites. So there were several problems, and in the community there's actually a watchdog that trying to monitor how different certificate authorities behave. And several certificate authorities were actually banned from this common list of trusted entities. And one of the biggest one is actually China Authority. I forgot the specific name, but this is China Certificate Authority was recently banned, at least in Chrome, because it did something bad. At least was caught to issue certificate to a website that the owner didn't authorize the certificate in the first place. And another kind of point of infraction here, I think you may have seen in the news, sometimes there's popping up information about, some manufacturer pre-installed certificate authority in your system. I forgot which company did it, but some laptop vendor, simply with operating system they given you like pre-installed, they also added additional certificate to this trusted authority. And what they try to accomplish is to effectively sniff all your traffic, because whenever you go to the website, they try to kind of steal your connection, redirect to the internal proxy server, and that proxy server would simply issue a certificate like quickly to whatever website you go into, and present that it's a valid certificate, and just try to communicate further. So being intermediary in this case gave ability to them to scan for viruses or do whatever they want with your traffic. So be aware if you ever see accidentally that someone tries to install a new certificate authority on your system, try not to do that, or try to figure out how to remove additional certificate authorities that give a lot of power to the guys who control that authority in the first place. The TLS certificate or HTTPS certificates can be in more than one state, obviously. So they can be valid, they can be expired, that's a basic thing. But there are more specific states, specific bad states that can exist. So for example, they can be wrong host. So for example, the certificate issued for Amazon.com cannot be used for the Google.com because it's a different domain name, and the browser will prevent you to go to that website. So for example, if some bad guy is trying to pose as Amazon.com or trying to redirect you to the Amazon.com, so all browsers will warn you about that. Some browsers just warn you, some browsers will completely prevent you to go there. Untrusted root. So this one I just mentioned, you can get the valid certificate for the domain name, but which is not trusted by your system. So in that case, the certificate should not be trusted by you because you have no idea who exactly issued that certificate. I mean, if you're setting up your own certificate authority, you can install that certificate authority in your system if you control. But if somebody else trying to install the new root, then it's actually a piece of warning. The certificate also can be revoked. So in some cases, and there's multiple cases when either somebody loses the private key, or we'll talk about the private key in the last module of the class. But in any case, there are some cases when a certificate authority is telling everybody, oh, this certificate no longer valid. Like, yes, I issued that before, but right now, please don't trust it. There's additional thing called pinned. So this thing is more like internal to the browser, and it simply means that the browser knows that this specific website has to have this certificate, and it will not trust anything else. So for example, if you're using Chrome browser, Chrome embeds a few certificates for the Google services, and doesn't matter what the kind of other authorities issue or not issue certificate for the Google.com, it will only trust these specific ones. And I have included this picture, and I would actually recommend you to go to this badssl.com and explore what exactly is happening, which trying to test your browser on different bad conditions of certificates. And as you may discover, even my browser that I'm using doesn't really catch all the bad conditions. And there are many, many different conditions that you can learn more about when you go to this website. To give a summary of today's lecture, just to highlight, so we covered cookies, we covered proxies, we covered the HTTP2, we covered the QUIC, and we covered HTTPS. And regarding the cookies, what I can say, the protocol itself, HTTP, is stateless, but it embeds ability to do application state. So it's kind of a little bit contradictory statement, but the protocol at the kind of protocol level is stateless, but the application on a higher level can embed additional state if it's willing to do so. HTTP is data-centric protocol. So kind of everything can be referred by URL, if you forget for a second all those cookies and other stuff. And with that, it can be explored using for proxying, or like for the caching at the local side, at the remote side, at the intermediary side. We'll talk more about the content delivery networks in one of the next parts. So HTTP is evolving, and I talked a little bit more of the problems about 1.1, how it's fixed in HTTP2, and how some of the problems that were not fixed in HTTP.2 were fixed in QUIC. And we just talked a little bit about different things. And HTTPS, so you definitely should learn a little bit about HTTPS from this lecture. Or at least I hope I raised some of the awareness of the HTTPS. So like, don't blindly go to the HTTPS website when something pops up. Don't blindly accept everything. Just try to understand what kind of, if you have some message popped up, try to understand what this message is about, and don't try not to install any additional CA trust roots. Otherwise, you may get in big trouble. Okay, so that's it for this module. So I hope it was interesting, like very knowledgeable for you, and see you later.